going to talk about COSMO, which is the Coronal Solar Magnetism Observatory, which is a hopefully future project. Thomas talked about, like, what does it take to get a project funded? Endorsement by a decadal survey is necessary but insufficient. We have that, and we've only been around for 15 years, so we probably have another 10 years to go through the cycle. Maybe we have to change our name a couple times, because right, DKIST was clear, then ATST and DKIST, so we're on our first name. Could be a mistake. So the challenge, we feel, important challenge, as Joan pointed out, we're all about the corona, is coronal magnetism being the missing link in our chain of understanding, key processes in the global solar atmosphere that cause space weather. That statement is due to Sarah Gibson. The photospheric magnetic field measurements are just not enough. You can extrapolate them all day and all night, and they're not going to really agree with the corona. And that corona is the source of space weather. So we really need to know about coronal magnetic fields. And we need to know about them synoptically. We need to observe them in the large-scale corona every day. And that's a big challenge. And that does not yet. That capability does not exist. So COSMO is this proposed facility that comprises three things. The K Coronagraph that Joan talked about that exists at Mauna Loa right now. This ChroMag instrument of Alfred Devine, which is under construction at HAO. And a large coronagraph. And this is the proposed part. It is a lens-based refractive coronagraph, 1.5 meter aperture, which is what you need in order to collect enough photons to observe the Zeeman effect in the corona. The corona is much fainter than the solar disk. The magnetic fields are very weak, of the order of a few Gauss. In order to get enough signal to noise, you need a large aperture. Coronagraph, DKIST will be a large aperture coronagraph. But later on, I'll talk about why these two instruments are extremely complementary. This is a 1.5 meter aperture refractive coronagraph. As I said, the really important thing about this one is it's got a 1 degree field of view. It's got an enormous field of view, which is really very important to capture that global view of the corona. The plan is to operate it synoptically. It has a refractive objective in order to achieve low scattered light. A lens scatters significantly less light than a mirror does. And the spatial resolution is about 2 arc seconds, so it's not anywhere near the regime of DKIST. And the plan is to do imaging spectroscopy and polarimetry, Stokes IQUV imaging spectroscopy with a narrowband tunable filter, similar to the one that COMP employs. This one, though, needs to be quite a large aperture and have a very large acceptance angle, which is a real challenge. But with the upgraded COMP, Joan mentioned, that has a lithium niobate-based birefringent crystal tunable filter. So we've demonstrated that now. So what do you get from imaging spectroscopy? Why do we want to go this route? Well, one thing is by observing different emission lines, you can get information about plasma temperature and density. There are lines that their ratio gives you density information, and the formation temperature of different lines tells you about temperature. The line of sight velocity tells you the Doppler effect, so you can learn about flows. And something we observe with COMP are waves. There are ubiquitous waves in the corona that are very important, indeed, also as a diagnostic of coronal magnetism, because the wave phase speeds tell you about the magnetic fields. The linear polarization tells you about the topology, and Joan showed some examples. And a lot of work has been done by Sarah Gibson and other people on exploiting that linear polarization, both the degree of linear polarization and the azimuth, the plane of sky azimuth that you can get by the arctangent of Stokes U over Q. So that turns out to be very sensitive diagnostics of magnetic field topology. So far with the smaller instrument like COMP, we don't have enough aperture to really measure the Zeeman effect, but with larger aperture telescopes, one can measure the Zeeman effect, which it's 10 to the minus 4 per Gauss in terms of the ratio of Stokes V to Stokes I. So it's an extremely small, one needs a lot of photons in order to have the sensitivity to measure the Zeeman effect in the corona. And as I said, the Alfvénic waves are really important because they give you information on the transverse component of the magnetic field. The Zeeman effect, of course, is line of sight component. Since the waves are propagating transversely, these Alfvénic waves, they give you information on the plane of sky component of the magnetic field. And they are more sensitive in some sense than the Zeeman effect because they're derived from velocity, which is like I in the blue wing and I in the red wing of a line. It goes as the intensity, whereas the Zeeman effect goes as Stokes V over I, and V is very small. Joan mentioned we had this prototype to sort of learn how to do this imaging spectroscopy. It was called the Coronal Multichannel Polarimeter, or COMP. And the lower left, there is showing 5 tunings of the transmission of the LEO filter that has liquid crystals in it in order to tune it across emission lines. COMP operated at iron 13, 10747, 10798 angstroms, and it also worked at 10830, helium 10830. And the full width half maximum of the filter is 1.4 angstroms. So the diagram on the right is showing you the optical setup in COMP, and it operated behind a 20 centimeter coronagraph that was one developed by Ray Smart at Sac Peak called the one-shot coronagraph at Sac Peak. And COMP was originally deployed at Sac Peak, where we got the bugs out, and then we moved it to Mauna Loa, where it operated for about 5 or 6 years. Maybe Joan would tell me that. And as Joan said, we're in the process of upgrading that to a filter that will observe 9 different lines now from the green line all the way out to 10830 with a lithium niobate base. This one has calcite in the tunable filter. But both have liquid crystals to tune the bandpass. Linear polarization is indeed sensitive. On the left is the degree of linear polarization that COMP observed of the 10747 line. Just basically Stokes Q squared U squared square root over Stokes I, the degree of linear polarization. And you can see a lot of dark places in the corona. And this is due to the fact that either the magnetic field is pointed towards you and there isn't any linear polarization, or more likely caused by the Van Vleck effect, where the angle between the radial and the direction of the magnetic field goes through 57 degrees, this magic number. And on the right is this azimuth, the direction of the magnetic field that one observes by taking the arctan of the ratio of Stokes U over Q. So these are very sensitive to the topology of the magnetic field, and a lot of work has been done now on people employing this information. This is an interesting thing. This is a comparison of an extrapolation by the PSI MOS model. The COMP data is on top, the degree of linear polarization and the azimuth left to right. And below is what is seen with the MOS model. Now, if you look, like in this region of the corona, it agrees really pretty well. And you think, gosh, so we can just get by with photospheric magnetic fields. But if you look on the other limb, it's enormously different in both the degree of linear polarization and the azimuth. I think a lot could be learned by modelers if they were to compare their models with, and this is a state-of-the-art model. I'm not trying to diss that, but I think a lot could be learned by modelers if they compared what their models predict with what is observed in terms of linear polarization, which we can measure pretty well right now. This is from Sarah's 2016 paper using this forward code where she integrates models over, does a line of sight integration of models and compares them to observations. Yuhong, I don't have a movie because this is just an Adobe PDF, but Yuhong did some simulations where she took her model and computed what would be seen by different kinds of coronagraphs, again, integrating over the line of sight. And this was a flux rope that erupted, of course, and indeed she verified that telescopes like the COSMO Large Coronagraph that we proposed, the 1.5 meter, and DKIST should be able to see the buildup of non-potential field prior to CME eruption. So this is going to be very interesting if we can observe Zeeman effect and with DKIST and hopefully build COSMO and observe it over a large field of view all the time. And so this was, refer to Yuhong's paper, and there's some great animations that she has of what we expect to observe. So we really believe that we can do this with enough aperture. I want to mention these Alfvénic waves. They're ubiquitous. We see them everywhere all the time in the corona, and they are important because, of course, they contribute to coronal heating, we believe. They may be important in accelerating the solar wind. And very importantly, the Alfvénic wave phase speeds can be used to infer the magnetic field. And that is very complementary, as I said, because the waves give the transverse component where the Zeeman effect would give the line of sight component. One has the potential to observe the vector magnetic field in the corona, I think, by employing both Zeeman effect and wave observations. The waves are primarily around 5 minutes that we see them, and they are related, I think, they're pumped by the solar acoustic oscillations underneath. I show an equation. This is not the equation we use when we invert for the magnetic field with the waves, but you know, the waves go as, you know, linearly, the phase speed goes linearly as b and inversely as the square root of the density. So one can get, if one has density, which we can get now with the ratio of the 2 iron 13 lines we have, then one can infer the magnetic field from the phase speeds. And we do have the ability to measure phase speeds with comp data. And this is a figure from a recently submitted, like on Tuesday, publication led by Zihao Yang and a large group of people using comp wave data to infer the transverse strength of the magnetic field, which is shown on the left. There's some red boxes that has to do with something in the paper. You can ignore those, but you can see there's a very detailed mapping of the transverse component of the magnetic field from the waves. The wave strength is between 0 and 5 Gauss inferred from this. So very, very weak fields, which is about what we expect. On the right are the errors that we've derived. And you can see the errors are non-uniform. That's because the coronal brightness is not uniform. And you do better when the corona is bright, of course. But the errors go from 0 to 0.3 Gauss, we believe. So measuring velocities is a lot easier than measuring the Zeeman effect. And one can get a good measurement of the transverse component of the magnetic field, a precise measurement. So this is very exciting, and we're hoping to enlarge the field of view for these measurements with the upgraded comp instrument. So why do we need COSMO, the COSMO Large Coronagraph in particular, in the era of DKIST? They're completely different things. Yes, they will both look at emission lines above the limb and observe the Zeeman effect, but COSMO is a synoptic instrument with an enormous field of view compared to DKIST, especially compared to DKIST with some of its post-focus instruments behind it, like the Cryo-NIRSP has a half arc second by 3 arc minute slit, which is a very small field of view. We have a 1 degree field of view that we can center on the sun and also have offset above the sun. And it's something that's going to observe the corona every day, every clear day as possible. So it's a completely different kind of instrument than the DKIST. It's more, I think, akin to the LSST as a solar telescope. It's a large synoptic survey telescope. And so, why do you need LSST in the era of, the Keck or something? Because it has a different kind of mission and a different field of view. LSST has an even more enormous field of view than the COSMO Large Coronagraph. So the combination of large aperture and large field of view, the product of those things is the throughput of a telescope. The COSMO Large Coronagraph is a high throughput telescope with a large field of view, 1 arcsecond pixels, 2 arcseconds resolution, so not really anywhere near the fine details that will be uncovered by the DKIST, and that's why those two are extremely complementary. So in conclusion, I want to say, we believe imaging spectroscopy with a large aperture coronagraph, synoptic, and the COSMO suite will provide these unique observations that will allow us progress towards understanding and predicting the causes of space weather. So my second conclusion, aptly, I would like to express my gratitude. I remember Michael and I go back at least 30 years. When I walked into HAO, I think Michael was there, or I was there when you walked in 31 years ago or something. So going on 32 years. So I've known Michael, and we became quick friends back then. And I would like to express my gratitude to Michael for his support and friendship, support as director and friendship before and after over the past 30 plus years. So thank you, Michael, very much. Michael's support of COSMO has been very important in its development, I should add. So thank you very much, and thank you for inviting me for this talk.